Okay, guys, let's start our lesson with a simple revision or quick revision about the previous lesson. Last lesson we spoke about concentration or the relationship between the concentration and the reaction rate. And we said for the reaction that involve solutions, the more concentrated solutions, the faster the reaction is. Because we have more molecules there, so the reaction will be faster. So today we will study about the relationship between the temperature and the reaction rate. So I needed to think, like, when you're cooking a food or when you heat something, cooking, because cooking is a reaction, okay, not heating. So what is the effect of high temperature on cooking food? So what do you think? Is it going to be faster, like for cooking? Is it going to cook the food faster or not? So can you tell me your suggestions?
Sorry, can you repeat the question again?
I was asking about your suggestions. What is the effect of high temperatures on cooking food? Yes, Sophie? Sophie, your connection is a little bit weak. I couldn't hear you. Your connection is weak. Can you repeat, please?
I said if the temperature is higher, the food will cook faster.
Okay, thank you. Salma, do you have another opinion?
No, I don't think so. I have the same opinion.
Okay. When you cook food, for example, if we boiled vegetables in hot water, boiling water, which is 100 degrees Celsius, okay, and we have the same amount of the food or vegetables in oil, okay, the boiling oil can reach 20 degrees Celsius, so it's much higher, okay, by 100 degrees. We will notice that the frying vegetables is going to be cooked faster than the boiled one. So what is the reason that the temperature, the high temperature that can make the reaction faster? We will have a simple investigation. Sorry?
Because like as you said, the oil has like a higher rate like of like degree of like heatness, like
Okay.
that's why like
okay, but what's happening exactly? Okay, let's take a look over the particles here. Let's explain about the particles. What's happening to the particles? We said concentration, okay, is giving more molecules or more atoms to the reaction, adding more atoms to the reaction that increase the reaction rate. So we have more molecules to react. Okay, good morning, Mohammed. Okay, so what's happening with the temperature here? We have an investigation, okay, we will investigate rates and the temperature. So reactions happen when moving particles collide, right? When they collide together, they will react. Okay, let's have a simple example about colliding and increasing the temperature. They said here at higher temperatures, the particle move more quickly and collide more frequently. Okay, our example is ourselves, okay? Let's take that if I have, let me draw this for you, okay? If I have here two people, okay, for example, okay, and I have guests here, okay, plenty of people. So I have a serving table and I have food here. I want to serve my guests. So I will have this food, okay, and pass it to my colleague or my friend, and my friend will give one by one, okay? This will take time, but it will be faster than if I am alone, okay? If I'm serving alone. Okay, I want to serve the guests more quickly. I don't want them to wait. So I'm gonna add or increase the number here, okay? Increase the number. Increasing the number, it's the same thing with increasing the particles, right? But I will explain about the temperature here. Okay? Our movement, okay, our movement as like too many people, okay, too many servants, okay, we will pass the food to each other faster, okay, faster. We will serve it faster. So this is an example for temperature. The particles here, for the particles, for the higher temperatures, the particles will move quickly. Why? Because they have more energy to move, okay? They have more energy. They got more energetic, so they will move quickly. When they move quickly, what will happen to them? They will collide, okay?
They will.
So when they collide with each other, this is where the reaction is happening now. Is it clear? Guys, is it clear?
I guess so.
No, not guessing.
When you explain more,
Sorry?
I feel like I got the point, but there's like I still need more explanation.
Okay.
Okay.
About what exactly?
Like the particles, like the whole thing that you just explained right now.
Okay, let's
But like it's okay.
have a pan of water, okay? And we have particles here. Okay?
Okay.
These are the water particle or liquid, oil, anything, okay? Here, I have a fire, okay? Like a low temperature, okay? The particles will start to move in and out of each other, right? And start to escape. So they will get energy from the fire to the pan, from the pan to the liquid. The liquid particles will start to move in and out of each other, okay? I want the food here to be cooked more faster or faster, more quickly. So I will increase the temperature, okay? If I'm increasing the temperature now, the temperature of the liquid is increasing, what might happen to the particles here? Are they going to move at the same speed or not?
No, they don't move at the same speed.
So they will move faster, right?
Right?
Okay, when they move faster, this is a particle and another particle, this particle will hit, will collide, that means touch the other one much faster, okay? So here is the reaction. The reaction is because the colliding of the particles. When the reaction is happening or happens when the moving particles collide with each other, okay? When they collide, this is the reaction. So they will form a compound. They will join to each other, atoms together, and form another compound. The raw food is different from the cooked one or the ripe ones, right? Because it's forming another thing. You cannot get it back. So this is a reaction, okay? This is a reaction. You formed another compound, which is the cooked food or the ripe food, okay? So here, more energy, which is more heat or more temperature, will make these particles move faster. So in this case, they will collide with each other much higher or much quickly or much faster, okay? More faster than the low temperature. When they collide with each other, they will react together faster. So this is the relationship between the temperature and the reaction rate. Is it clear now?
Yeah.
Okay. We have here an example about sodium thiosulfate, okay? Sodium thiosulfate. So I have sodium thiosulfate, okay? And I added hydrochloric acid, okay, to it. So I will get sodium chloride, water, sulfur dioxide, and sulfur. Okay, this reaction, you have to know something about this reaction, okay? In reactions of solutions, okay, aqueous solutions with acids, like sodium thiosulfate here is a solution, okay? But hydrochloric acid is an acid. So if we want to mix or if we want to react aqueous solution, or let's say water, okay, and hydrochloric acid or any kind of acid, always we should add the acid to the water, not the reverse, okay? And this is for a very important reason, okay? Because there is a hazard of adding the opposite. If we added the sodium thiosulfate to the acid, explosive, okay? Can splash, can explode, can like destroy the, destroy anything, like can splash in the eyes or harm the person. So always never add the solution to the acid. No, we have here the solution, then we should add the acid on it. The reason is that acids always releases energy, which is heat, okay? We have an example. We have the bleach that we are using for cleaning, okay? Or removing the stain from clothes, okay? Like Clorox, for example, okay? If you touch it with your hand, you will feel a little bit heat on your finger, okay? That's because it's this is a very concentrated acid that can release heat. So if you added water to the acid will be concentrated, so it will release more heat. So in this case, it will get more, release more heat. So the solution may boil a little bit. So in this case, it will splash, okay? It will splash to the eyes or to the surrounding area. So this is an information you have to know and use it for the rest of your lives. You have to add the acid to the water, not the opposite. Okay, now I need you, okay, to give me symbols, okay? I'm gonna give you the symbols for the sodium thiosulfate. Sodium thiosulfate solution is Na2 S2O4, okay? This is my thiosulfate, okay? We all know this is hydrochloric acid, which is HCl, okay? I need you to find out the rest. So can you tell me, like, sodium chloride, what's the symbol for sodium chloride?
NaCl.
NaCl, thank you. And Mohammed?
NaCl.
Yeah, no, just a second. She said NaCl. What's the symbol for a sulfur dioxide?
Sulfur dioxide, S2O4, S2O2.
No,
O4, S2O4.
there's di here.
So it's 2.
It's not S2.
Oh, SO2.
SO2, sulfur dioxide, okay, sulfur dioxide. So this is the reaction of the sodium thiosulfate and hydrochloric acid. Okay, now I will share here, okay. There is a student that she planned for her investigation, sodium thiosulfate solution react with hydrochloric acid to make 4 products, which is NaCl, water, sulfur, and sulfur dioxide. Here the sulfur is formed as a solid, okay? We can see it cloudy as cloud, we are forming cloud clouds in the flask, okay, inside the flask. So what she did, she drew a cross over a paper, okay, and she placed the conical flask on it. She had the solution, which is sodium thiosulfate, down here in the conical flask, and she started to pour the acid on it. So here she got a cloudy mixture. She got a cloudy mixture, as you can see here in the conical flask, okay, which is like kind of yellow. Now, then what's happening exactly? The forming, how did she know that the mixture start to react? She found this cloudy sulfur forms, okay? The solid sulfur forms gradually, and then the mixture became cloudy, okay? And here she can no longer see the cross. So she was looking from up here. She didn't see the cross. So she knew that the cloudy substance is the product that she wants, okay? Then she did the same thing, or she repeated the same thing using different temperatures, 4 different temperatures. So she got, a second, give me my mouse, okay? Okay, she got different results, okay, and she recorded this in a table. First, she wants to use a table, and now, actually, is he, not she, whatever, okay? She was recording the results at different temperatures, 20, 30, 40, 50, 60. She got these records. So at 20 degrees, the first time, okay, of course, she repeated the experiment 3 times to look at the average, okay? So when she repeated the experiment 3 times, she got the average for 20 degrees is 242, and 30, 180, 40, 61, 50, 32, 31, 60, 15, okay? Now, what can you conclude from these results? Look at here at the average and the temperatures. So what can you tell me about these results?
That
When the temperature is lower, the average is higher.
yeah.
Sorry?
When the temperature is lower, the average is
It
higher.
is higher.
Okay.
But
Mohammed?
the time takes more.
Mohammed?
Can you repeat? The internet was disconnected.
Can you look at these results, okay, and the temperature, and tell me what can you see here?
As you go down, the temperature decrease. As the temperature increases, the average decreases.
Okay, what can you tell me about this?
For this reaction, like if the temperature is lower, it will react faster.
Lower?
Yes.
Here the temperature is high, okay? The temperature here is high, is getting high, okay? The reaction time is decreasing. The reaction time is decreasing.
So if the temperature is higher, the reaction time will be less.
Of
It
course.
will be
Yes, why? Because we said at higher temperatures, more atoms or more molecules will collide, or particles will collide together faster. So the reaction won't take time. It will decrease. As I am increasing the temperature, the reaction will happen faster. Okay? Is it clear?
yes.
Okay, so this was his conclusion, that the graph here, okay, his graph here showed him the correlation between the temperature and the time. When he started to increase the temperature, the time was decreasing. So he was getting his reaction much faster. So this was his conclusion, that at higher temperatures, the faster the reaction. Now I need to see what is the relationship between the surface area and the reaction rate. So at higher temperatures, we said, as we increase the temperature, the reaction rate will be faster. Okay, what about the surface area? Okay, if the surface area of the particles big, is it going to decrease or increase the rate of the reaction? So here we have the reaction of dilute hydrochloric acid with calcium carbonate, okay? So here the calcium carbonate plus the hydrochloric acid gives us calcium chloride, carbon dioxide, and water. Guys, can you tell me or remind me, what is calcium carbonate here? What do we call calcium carbonate? We're using it for buildings.
Calcium carbonate.
Yeah, we studied
Is
this
it the
before.
cement?
No.
What is it then? Gyps.
No. It's the marble, okay? It's the marble. So calcium carbonate, when we add hydrochloric acid, okay, calcium carbonate plus hydrochloric acid, we will get calcium chloride. What is calcium chloride? Is it a solution or a solid or what exactly?
It's a
Isn't it a salt?
Yeah, it's a salt, okay? So we
Yes.
will get it as a salt. Plus carbon dioxide as gas, and we have water, we can get the calcium chloride by evaporation. So here, we have 3 samples of calcium carbonate, okay? One of them is, let me get the pencil. Okay, we have 3 samples of calcium carbonate, okay? Sorry, the same amount, okay, of calcium carbonate. One of them is powder. The other one is small lumps. The third one is big lumps, okay? So here I have conical flask with hydrochloric acid, okay? If I added the calcium carbonate, guys, can you remind me of the symbol? Ca?
Ca.
CO2.
It's dioxide.
Wait for the carbon dioxide.
No, I need calcium carbonate.
CaC3.
CA3.
Sorry?
CaC3.
Ca?
3.
This is calcium. There's nothing called Ca3. This is calcium. What is carbonate?
C3.
No, this is carbon. And even not 3. CO3. Do you remember 8? What does it mean? That means there is an oxygen in this compound. Carbonate, sulfate, nitrate, nitrogen with oxygen, sulfur with oxygen, carbon with oxygen. This is the meaning of 8, okay? So here, oh, sorry, okay. I have here HCl, okay, hydrochloric acid, and I will add 1 by 1. If I am adding, okay, the big lumps to the hydrochloric acid, okay, what do you think you might see? Is it going to be fast or slow?
It is going to be slow.
Okay, let's say slow. Okay, what about the other one, the small lumps?
They will react faster than the big lumps.
Okay, faster. What about the powder then?
It will react the fastest.
Very
So,
fast.
much faster, okay? Okay, can you tell me what is your explanation here? Why the big lumps is reacting fast, but the powder here is reacting much faster?
Is it because of the size of the
Yeah,
size?
because like when it's
Wait.
smaller,
Mass
so when it's
weight.
smaller, the particles will they will react faster with
Yeah.
the hydrochloric acid.
Yeah, thank you, Sophie and Naim. Okay, this is because of the surface area, okay? The reaction is happening at the surface of the lump or the particle. Let's say this is the particle, okay? Sorry, not this one. This is the particle, okay? If the particle is big, okay, the surface will react with the acid here, okay? Will react with the acid. If I'm smashing it, okay, what will I have? I have more particles. I have more particles to react. So if I'm decreasing the surface area, I will have more, I will increase the reaction rate. The reaction will happen faster, okay? So as surface area increases, the time for the reaction decreases. So therefore, increasing surface area will increase, increasing the surface area. Oh, sorry, I have a mistake here. I meant to say decrease. Okay, this is decrease. No, sorry, not this one. Okay, here is decreasing. Okay, I meant to write decreasing. Okay, if I'm decreasing the surface area, I will increase the reaction rate. Okay, I will increase the reaction rate. Here, the explanation about this, what is happening exactly, okay? Here the particles, as I was explaining here, okay, the particles from hydrochloric acid, okay, the particles here in hydrochloric acid react only with particles of the surface of a piece of calcium carbonate. So as I was saying, the surface is reacting with the acid, okay, with the acid. So what happened when I smashed the calcium carbonate? For example, if I have 10 grams of calcium carbonate powder, I will get a bigger surface area than grams of calcium carbonate lumps, okay? So here, this means that the powder has more particles that are available to react. So here,
Like the particles are more spread out to react.
yes, I have more particles to collide, okay? I have more particles to collide. So I will give you an example, okay? I don't have much time. Let me erase this. I will show you a video that's how he did this. Where is it? Yeah, here.
Today we're looking at the different factors that affect the rate of a chemical reaction. What we're going to start off by looking at is the surface area, how that can affect it. And if we've got the same amount of material, if the particles are smaller, then we increase the surface area. So, for example, if we've got a lump of material which may contain 20 particles in total, it's only the particles on the outside which are available for immediate reaction. If you count them up, you'll see that there are just 16 particles that can react straight away. However, if we break it into smaller pieces, then all 20 particles are available for immediate reaction. So the reaction will be quicker. We can do an experiment to demonstrate this. Okay, this is the experiment. Here we've got 3 beakers, each containing dilute hydrochloric acid.
Guys, can you tell me here where is the changeable variable?
The amount of water.
No, there is
The
no
calcium
water.
carbonate.
There
The
is,
size of the calcium carbonate.
yeah, thank you. Size of calcium carbonate. And what is the controlling variable here?
The hydrochloric acid.
The acid.
The same amount of acid, the same type of acid, and the same type of the compound, the calcium carbonate. Okay?
And these containers have got marble in them. The chemical name for marble is calcium carbonate. Here the marble is divided up into fine powder. In this one it's relatively medium-sized chips. Here there's fairly large chips of calcium carbonate. Now what we're going to do is going to put them into the dilute hydrochloric acid and just by observing it make a note of the rate of reaction, how fast the reaction goes. In other words, how fizzy it gets. This is the one with the large chips. As you can see, the reaction's fizzing. It's not particularly rapid, but it's going fine. And the reaction shouldn't take too long to complete. With the medium-sized chips, however,
See here the reaction, the fizzing is happening more quickly, okay? So you can compare the third one with these two, okay?
you can see the reaction is much faster. And then we come to the powdered calcium carbonate.
This one is the fastest.
Very obvious
Yes.
to see that the surface area, increasing the surface area, increases the rate of reaction.
Okay, here look at this one, okay? At the one, can you see the arrow?
Yes.
Okay, where am I pointing here? The lumps here still reacting. They didn't disappear. That means they didn't use up yet, okay? Here the powder is getting like is disappearing, but now the small lumps. Here the powder is getting is disappearing much quicker, okay? So this is the the relationship between the surface area and the reaction rate. I have here something, I'm so sorry for this, okay? Here, okay, about this, okay? I said this is decreasing, right? Here, I was just like, I was confused between the size, okay? Here, I was meaning that decreasing, okay, the size of the particles, decreasing the size of the particles. That means increasing the surface area. So if I have this piece of calcium carbonate, if I smashed it, okay, if I smashed it into smaller pieces, okay, I will get more powder. I will get more powder, but it's with the same measurement. If I have, like, for example, here 10, this is the same thing with 10, but this is like a block and this is a powder, okay? So here I'm increasing the surface area, but decreasing the size, okay? Decreasing the size. So the surface area increased, okay? If the surface area increased, this is surface area increased, okay? The reaction rate will increase also, okay? Is it clear now?
Yes.
Guys,
Yes.
Yes, Miss, it's clear.
okay. So next time, okay, we will study about the last thing about the catalysts and reaction rate. What is happening if we use catalyst and how does the catalyst work? Don't forget the yellow box, guys. And if you have any question, we can answer it now. Guys, any question?
No.
No.
Okay, so see you next time in the new lesson, okay?
Okay,
Goodbye.
bye.
Okay, bye-bye.
Have a good day.